This is a low power, low noise amplifier. It saturates by 1 dB at -2 dBm. I'm running it now at -4.5 dBm in the interferometer, because I was interested in optimizing the flicker noise. But, as it turns out, I cannot do that because I cannot see the flicker noise because of all these spurs. So I will investigate and try to do something about this situation. To that end, I have an audio generator here connected to this thing, a bunch of ferrite rods with some copper wire around them. And I hold that onto the amplifier, and you can see, well, here is the carrier, and it's surrounded by sidebands ±100 Hertz. I don't know where they come from. Maybe there is a 100 Hertz field. I can see I have those 100 Hertz sidebands around the main signal here also. Anyway, screening this box for magnetic field, but that will not help, because when I put the magnetic field on top of the phase shifter, I also see this sideband. You can see on the S meter. And furthermore, if I place it on top of, let's say, this hybrid thing, we have a strong signal there also. And this 20 dB coupler, as it turns out, everything with a ferrite core inside it is a modulator when it's subjected for an alternating magnetic field. So the problem comes from everywhere, and there is no way I can screen properly for magnetic fields in this house. And moving everything outside with a laptop, that's not very attractive. I have simplified the interferometer greatly. There is the local oscillator, the black box, coming in here into a first hybrid. Upon the other side there is a 50 ohm resistor, and the output has a 3 dB attenuator in one leg that goes directly to another hybrid. And the other output goes through the attenuator, more attenuation, this one is continuously variable, and then the phase shifter, and from there through a fairly long cable to the other input of this hybrid. And then what is on the outside doesn't matter on the what comes after this, because there the signal levels are so low, so there is no modulation inside all the other stuff. So that's just low noise amplifier and impedance match and so forth. What I see on the screen is a significant amount of these spurs, as expected, because, for example, I have this one, which is very sensitive to magnetic fields, and also this one, which seems to be equally sensitive. And then this one, which for some reason is much better. And I don't know, I don't remember how these were designed, but I will have to open and look for the differences. Here is the good hybrid, and here is the not so good hybrid. Here I have copper on outside of the ferrite cores, and that is to increase coupling, to force the magnetic flux into the ferrite. And I have also filled these cores with copper wire. So that was not intended to reduce sensitivity for magnetic fields, but it has that side effect also. So I will take this apart and put a lot thicker copper outside the cores here. And I haven't decided what to do with this yet. One turn of 4 times thicker copper. This is 0.2 millimeters. The other one was 0.05. Well soldered all the way. I want a good shorted turn around the ferrite. And I put a second 0.2 millimeter copper foil, is it called that, copper sheet, on this ferrite, and I do the same with the other ferrite. 2 layers of 0.2 millimeter copper around the ferrites on top of what was before has made this one very insensitive. I don't see, or at least very little, of the field from this. But this other unit with another kind of ferrite, I still can see here there is a signal, and the level is something like minus 120. It was similar to the level I saw from the phase shifter before, and the phase shifter is something like 25 dB stronger. So it has been an improvement, but I should add 2 more layers of coppers on the ferrites in this, or maybe make another box. Anyway, worst at this moment is the phase shifter. And I also discovered that here there is some iron. You can see, I lift it and place it here. I think I used standard inductors with ferrite cores in this box. I have to put there instead air inductors. The phase shifter has a bifilar wound powder iron core. It was glued to the box before, but I removed that melt glue, and I will now wrap it in copper. This is now 4.5 turn of 0.2 millimeter copper, and I will solder all of it to make sure it is a good short-circuited turn for each layer of copper. Like this, and I will have a look from the other side. So I'm pretty sure this is a very good short-circuit turn around that will prevent magnetic fields from going through this hole. And finally I added 1.5 millimeter thick sheet metal from copper on both ends of this tube that I made from thinner sheet metal. And it will be interesting to see whether this helps. I have put that copper enclosure with its transformer inside in mu metal, but that didn't help very much. You can see when I come in with this thing here, here, and from beneath where it was more sensitive. So there is still some sensitivity, but it's not as bad as it was before. Compared to the other, this one is a little bit worse. Maybe easier to see on the S-meter graph. That's the hybrid. And this is the phase shifter. They differ by 5 dB or so. But I have a lot of spurs and I don't know the origin. So I will try to dig a little deeper into this. I have moved the interferometer from here to here. So now the distance to the computers is about 1.5 meters to the nearest computer and 2.5 meters to the one that is further away. This box here contains cables, a quarter wave, half of that, and stepping down in a factor of 2. It means that I don't have to use connectors with cables to set the cause phase. I can use those switches and then do the fine-tuning of the phase on this phase adjust. The result is I still have a lot of modulation from magnetic fields. Although I made some things to reduce the fields, what you can see here is at the bottom, which you don't see, there is a layer of mu metal to reduce the horizontal fields. It should help at 50 Hz a little, maybe not at 1 kHz. I don't know so well the properties of this thickness of mu metal. Then there are 3 layers. Then there is wood kind of thing, 20 millimeters, because I don't want to drill into the mu metal. I want to save that undestroyed. Then there are 3 layers of 3 millimeter aluminium. In total 9 millimeters of aluminium that will reduce vertical fields, at least near the center of this sheet, where the hybrids are located, here. And then I look at what I can see. I have a good balance, and here's the spectrum. The carrier is suppressed to this level, and we can see all the spurs. And I can check with this magnetic source, that coil with the ferrites, that I can see the interference, and I can see easily that the hybrids generate sidebands. But there is another problem that I can see now, and that is I have flicker noise. It means if I click here on the noise floor and read, I don't know what the calibration is, and that's not important for this thing. You can see this is the level, but if I click a little bit further away, 10 kilohertz or so, oh, I didn't save that level. Here, 10 kilohertz away, it says minus 182. And here, which is 500 hertz or so, well, 700 hertz, it is at least 5 dB more. So there is flicker noise, and probably that is also coming from iron. So next step will be to try to get rid of all the iron. This is an iron-free hybrid for 10 megahertz. I made 2 of them, and we'll see what happens when I insert these instead of those with iron in them. Now both hybrids are replaced by the iron-free ones, and modulation sidebands are significantly better. And also the color here is darker, means flicker noise has been reduced. So I will do the same trick with the phase shifter, replace that iron core with an air-wound bifilar winding. The phase shifter is now iron-free, and the performance of it, as you can see it here, upper is the impedance and lower is the phase, and I turn the capacitor. So I can turn by about 30 degrees, and this doesn't change the impedance significantly. Now there is no ferrite core in the interferometer, but I still have these modulation sidebands. They are weaker, but they are present. And the setup is sensitive to vibration. You can see when I'm speaking, something is vibrating. But right now I want to get rid of these modulation sidebands. So I have been using this bunch of ferrite rods with a coil on them to try to see from where modulation comes. And it comes from everywhere. Very hard, and I cannot do anything good by subjecting the interferometer by this AC field. But there is another trick. Magnetic modulation. I could use a DC magnetic field, I mean a permanent magnet. I have replaced the amplitude adjustment box with one that is mechanically much more stable, and now I can set the attenuation caused by the interferometer very high. Here I have some strong magnets, and if you look, here is the oscilloscope. The upper track is the output from the interferometer that is ideally 0, and as you can see it is fairly low. And I take these magnets and put them near but not in contact, and you see here, and I move the magnet back and forth like that, and this is what happens. So this connector is sensitive to magnetic fields. Reading specifications, it says gold on nickel. And all the modern connectors I have are gold on nickel. And they all cause this modulation problem, and connectors are everywhere. That's why I couldn't find where the modulation comes from with this magnetic field emitter. Now I put a cable here with old connectors with center pins from silver, and I have again balanced. Well, I have to redo that. Okay, here is the reasonably well balanced interferometer, and I put the magnets here, and there is still some sensitivity, but not as much. If I compare to this one, for example, well, these things are problematic. They have gold on nickel on the male contact as well as on the female contacts. I don't have old contacts with silver for chassis mounting. So it seems this is something I have to live with. Maybe this ferromagnetic phenomenon that gives modulation also causes flicker noise. Probably it does, but it's beyond my skills and instrumentation to find that and to quantify it. The interferometer is still running with this roll of coaxial cable as the device under test. I consider it a noise-free attenuator, about 1.5 dB. It means that what I do is actually to measure the properties of the interferometer. So step 1 is to establish the level of the carrier, where I have the SDR IP connected, and I have set it to show 0 on the S-meter graph. And then I have a second signal here, 2 kilohertz down, and I have set that to be 70 decibels weaker. So it's here, and you can see 69.988. So it's very close to 70 decibels below. And then I look for that signal in Linrad. Means here is the carrier, and I want 2 kilohertz down. So that is here. And this should show minus 70 now. And it shows minus 69.74. So I have to do a small adjustment. Here the separation is 70 Hertz in a bandwidth of 20 Hertz, where there is a region without any obvious modulation spurs. And the level I see is minus 169.6. And applying attenuation, you can see that the noise is much lower, so I don't have to take it into account. This is a separation of 10 Hertz in a bandwidth of 1 Hertz. And the level I see then is minus 174.4. Now I'm looking at a separation of 50 kilohertz. And here the noise is minus 165.83 in a bandwidth of 1 kilohertz. And I insert this attenuator, and it doesn't make any difference at all. If I read it on the S-meter graph with this readout tool from here to here, it says minus 165.9. That's 1/10 of a dB, and it's probably not significant even. It means that what I see is not sideband noise. It's the white noise of the low noise amplifier after the interferometer. Here is the limitations given by this interferometer. B0 is minus 164 dBc per hertz, and that's the sum of phase noise and amplitude modulation noise. dBc per hertz upwards, and on the horizontal scale it's the log of the frequency. 0 means 1 Hertz, 10 Hertz, 100 Hertz. And at 1 kilohertz the flicker noise is the same as the flat noise from the amplifier after the interferometer. So now I'm prepared to start to look at some two-port devices, attenuators, amplifiers, capacitors, resistors, whatever. And particularly I will want to look at limiters, because the oscillators I have a lot of close range noise. And maybe that comes from flicker noise and the limiters I'm using. We will see.